So welcome back to the Physics Lounge. We're looking at the Level 3 Physics 2022 electricity paper for the exam. So George is investigating AC circuits. A whole bunch of information given to you there. Just note that everything's in three significant figures as usual. So your answers will most likely be in three significant figures. And the first part of the question says show that the reactance of the capacitor is 58.9 ohms. So remember XC, the reactance of the capacitor, equals 1 over 2 pi FC, or 2 pi f can be exchanged for omega, but omega is 2 pi f. So we just plug those numbers in basically, and it's a show question, so you expect to use that number a little bit later on in the paper. B says calculate the circuit current. So we would have to use RMS values here. So we're likely going to use V RMS of the supply equals I RMS, which is your circuit current, that's the one you're trying to find out, times Z, the overall impedance of the circuit. V equals IR, but using the supply, VS RMS, and the overall circuit impedance. So you have the voltage of the supply. You can rearrange for I, of course. I equals V over R, or I equals V over Z in this case. How do you get Z? Z is the sum of the resistance squared plus the capacitance reactance squared and then square rooted. That's because Z is the vector sum of R and XC. So you add those two to get Z. You can shift your XC down to that side, and you've got the usual triangle and all of that. Once you've got Z, plug it into the equation. V Z. That looks like a 2 on its side, but there we go. And then you can plug the numbers in. C is calculate the phase difference between the supply voltage and the circuit current for the circuit. You may draw a phase diagram in the space below. So in this case, remembering your old civil, the voltage and the capacitance lags the current, and the voltage in the inductor is led by leads the current. So you've got your where are we? Voltage across the resistor here, voltage across the capacitor here. So you're going to find voltage of the supply, which we know the voltage of the supply, but we're after that phase angle. Excuse me there. And so we know. How much information do we know to form this? So we're going to have to just rely on the phase difference. Excuse me. So this angle will map over to the impedances as well. So if you've got, I'll sketch another little, you've got R here, you've got XC here, and then you've got Z here. So we know XC, Z, and R. So that angle between XC, Z, and R is going to be equal to this angle here. So those two angles are the same. So that's really fine. That means we can do that calculation because, as I said, we've got R, we've got XC, which is down there, and we've got Z, so it's no problem. So finding the angle using a bit of trigonometry, and then what was the question again? The phase difference, and state which one leads. So which one leads? Current always follows the voltage across the resistor in the circuit. It just has to, because the resistor is that kind of passive component where you stick a voltage across it and a current will flow. So we can work out the magnitude of the current with any of these relationships. V equals I times R, VR equals I times R, VS equals I times Z, and VC equals I times XC. So those will all give the magnitude of the current, but the phase of the current always follows the resistance. Excuse me. And because it's a rotating vector in that direction or around that direction, we know that the current there is going to lead the supply voltage. It's going to peak first. It's going to hit the top first, so it's peaking first. It's leading. Okay. Oops. What's going on here? My cursor was doing funny things. Okay. It's probably an operator error, eh? Explain how the addition of a suitable inductor to the resistor capacitor circuit with the AC supply can make the circuit resonate. Begin your answer by explaining the meaning of resonance in a circuit. So resonance is when you have maximum current flow in a circuit, and this comes about by having minimum impedance, and minimum impedance just means that your capacitor and your inductor are, because they work in XL, XC, and R, because they work in opposition to each other, when they are equal, then the voltages across them will be equal in magnitude. And those are in opposite directions, 180 degrees phase difference. So they oppose each other, cancel each other out, and you're only left with the voltage across the resistor. And of course, if Z is minimum, because of those two working against each other, then your current will have to be maximum. Excuse me. So how the addition of an inductor can work to do this, I've sort of talked around a little bit. You have to have the right value inductor to make XC equal to XL. So 1 over 2 pi FC must be equal to 2 pi FL. I don't know if they give you, let's have a really quick look, in your resource, the equation for, oh they do, yep. So the equation, which you can work out from calculating this anyway, they say for the frequency of resonance is 1 over 2 pi square root LC. So yeah, again, and classic application is for a receiver circuit, like in a cell phone or a radio, anything that transmits and receives wirelessly, and in your antenna, and you want to tune your antenna to a particular frequency to maximize the signal that's coming in, and to cancel out all other signals, because there's so many different signals waving around through the air. That's a really bad way of describing it, and you need to be able to amplify the one signal that you're interested in and convert that to sound or a person's voice on a phone or whatever it may be, your internet signal. Have I answered the question? How the addition of an inductor can make the circuit resonate? The meaning of resonance: maximum current through minimum impedance, where XL and XC, that's meant to be a C on the bottom by the way, equal. Maybe there's a more technical definition, but you get the idea. And yeah, no, fine, we'll move on. I'm just going to take a short break from my voice, but you won't experience a break except maybe a small pause, and then we'll carry on. Okay, David is investigating inductors and magnets, uses a 1.60 Henry 22.0 ohm inductor. So it's interesting, you don't normally get given the resistance in that form. You'd be tempted to think that that's the reactance of the inductor, But remember, it's a DC circuit, which we can see from the circuit below, and we can see the 22 ohms is more like the internal resistance of the inductor or the resistance of the circuit. Kind of high for internal resistance though. But anyway, 12 volt supply. The inductor is considered as a pure inductor in series with the resistor. Why they say pure inductor is so you don't have to worry about any other resistance in the circuit, just the 22 ohms. It says calculate the circuit current after 2 time constants once the switch is closed and the current begins to flow. So remember, your time constant for a inductor is L over R. Oh. Okay, yep. So we know the inductance and we know the resistance. We plug those numbers in, we get the time constant. We don't actually need to calculate that, because after 2 time constants, we know there will be 63% change of the available change for each time constant. So then we've got 63%, and then we've got 63% of that remaining 37%. So 63%, and then 63% of the remaining 37%, and whatever that is whatever it is. Do we know the initial current in the circuit? So what are we, once the switch is closed and current begins to flow. So we're going from 0 to the maximum. So a little sketch over here, really badly drawn diagram. 63% change, so it's going to go up something like that to the maximum. Current maximum in the circuit is going to be just V of the voltage supply, 12 volts, over R. I equals V over R, R being the 22.0 ohm resistance, because once you've reached a steady state in the circuit, the inductor is doing nothing. So I equals Vs over R. And so that'll give you a maximum value, 63% of that, somewhere in this range up here. And then you've got another 63% of the available. So visually, that's what you're looking for. You can do it as whatever that current is. It would be 0.63 I max. That would be your first value there. And then you would have to add to that 0.63 of 0.37 IMAX, just to put it in a really awkward way there. B, state the voltage. So state says we're not going to do some calculating, but state the voltage across the pure inductor and the voltage across the resistor once the current is steady. So that would have been a nicer question to have first, just to lead you into it. But yeah, in any case, voltage across the pure inductor, once the current is steady, it's 0. Voltage across the resistor is going to be the 12 volts. So this is a bit silly actually asking that, frankly, because you can't do the question beforehand without that. Yep, anyway. And it should be assumed, you'd be pretty obvious if you're marking this, what you're calculating and why you're doing it, but maybe it's worth stating it explicitly. Once the current has reached a steady value, the switch is open and the current falls to 0 in that time. Calculate the size of the average induced voltage and state the direction of the induced voltage across the inductor. So this is where we're getting into Lenz's law, Faraday's law. So Faraday's law is going to give us the magnitude of the induced EMF, or induced voltage across the inductor. EMF equals negative L times the change in current. Remember, it's going from its maximum that we calculated before, which we would have, but I didn't, but you know, I over the change in the time. So you're given the change in the time, you have the current from before, the inductance is given to you, so that'll give you the magnitude of the induced voltage. And then the negative here, Lenz's law indicates the direction, which should be opposite, like it's going to try and support the oops, I I've done something. Is that still working? Yeah. I don't know if anything popped up on your screen, but I had a button and it popped up here. But coming back to Lenz's law, it's going to try and support the current flow in the direction that it was travelling before it tried to switch off. So the negative just says that it opposes the change that produced the voltage. So it's going to go in the same direction as the normal circuit. It's going to try and push a current around in that direction, conventional current from positive to negative. Hopefully you remember that the long line is positive and the short line is negative. So that gives you a direction there. Oops, I think I'm leaning on the screen. That might be causing problems. D, the 22.0 ohm resistor is replaced with a 44.0 ohm resistor and the switch is then closed. Explain by comparing quantitatively, so how much the changes that will take place for the size of the maximum current. Well, that's going to drop because I equals V over R for your maximum current. V is your 12 volts, R is increased. It's doubled in fact, so it's going to halve the current. So you'd actually specifically have to say that it's half to get full marks on this, since you have specific numbers that you can work. So I goes to half I. What's going to happen to the time constant? Time constant equals L over R. So again, time constant, you're being divided by a bigger number. Time constant is going to halve. Is that right? Yep. If it was a capacitor, T equals RC. If you double the resistance, you're going to, or for the same capacitance, you're going to double the time constant. For a resistor, for an inductor, so we're not doing a capacitor, but sometimes helpful to compare in your thinking. If you double that, because it's being divided, you're going to halve that for the same inductance. So time constant goes to half time constant, means it'll go quicker. It'll reach the steady state quicker. Yep. And then the energy stored in the inductor once the current is steady. So again, E equals half L I squared. That's your energy stored in the inductor. So half is a constant, L is a constant. I, what do we say? I goes to half I. So half I, all of that is now squared. So you're going to end up with 1/4 the current, or 1/4 for that portion. So energy is actually going to go to 1/4 the energy in the circuit, just because of that squared factor. Okay, question 3, capacitors in DC circuits. Anne is carrying out some experiments using parallel metal plates to investigate capacitors. She takes a pair of metal plates with an area of 0.160 meters squared, connects to a 9 volt DC supply. The plates of the air-filled capacitor, so there you go, epsilon of the air 1.00, are separated by a distance of 1.0, that looks like 1 millimeter. Show the capacitance of the capacitor is 1.42 times 10 to the negative 9, so C equals epsilon naught, epsilon R area divided by D. Just plug your numbers in. Epsilon R is 1.00 from there. You're given all the other values. Epsilon naught will be in your resource, the absolute permittivity of free space. And you should get that value, which you'll probably have to use later, because again, it's a show question. Calculate the the energy stored in the capacitor once it's fully charged. So energy stored in the capacitor equals half QV. Do you have Q? No, but Q equals CV. And you know the voltage across the capacitor will be the voltage of the of the supply once it's fully charged. Which was it? It was 9 volts, wasn't it? Yep. Excuse me. Having some voice issues. We'll get through to the end. So we know the voltage we know the capacitance, which was given above. So we know Q. So if we know Q, we know again the voltage, or you could combine those two together to have E equals half CV squared, and that would give you the energy stored in the capacitor. Describe the effect on the energy stored in the capacitor when a sheet of mica with a relative permittivity of 7.00 is introduced between the capacitor plates. Well, that's going to increase the capacitance. because now if I come back up to here, that epsilon r, the dielectric constant for that is increased. So you've increased by 7 the capacitance. So what's going on here? There we go. I was leaning on the screen again. So the effect on the energy stored. So you've increased the capacitance by a factor of 7. When you increase the capacitance by a factor of 7, I'm going to combine those two equations so you can see directly. So E equals half CV squared. The question we have to ask is the voltage changing at all? And the answer is no, because that's still determined by the supply. And we're talking about the energy stored when it's at a steady state in the circuit. So the voltage across the capacitor will be unchanged, still the supply voltage. But the capacitance has gone up by a factor of 7, so the energy stored will be going up by a factor of 7 as well. I think that's what they're getting at with there. Okay, C, and then disconnects the plates from the 9-volt supply so the plates are electrically isolated, then pulls the plates apart. Oh, one of these questions. Explain what would happen to the charge on the plates and the voltage across the plates. So as an interesting kind of approach, you've got the same amount of energy stored in there. And if we stick with the half QV, the charge cannot change in there. But, and you would think that the energy doesn't change, but the energy that will actually change because you're inputting energy by moving the plates apart. So you're adding energy to the circuit. You think like you've got two magnets and you pull them apart. You've introduced some potential energy because they're trying to come back together. So you've increased the energy. So so the charge doesn't change. Energy has to increase because you've inputted energy. And the voltage will therefore also have to increase, which is an interesting consideration. None of that would seem possible unless you're putting energy into the system. It's a bit of a tricky question, actually, if you're not used to that kind of stuff. So I'm not used to it, and it gives me pause as well. But it's that's what's going on. You could kind of go back to your level 2 kind of stuff there, but even that's not going to help you that much. If you remember, you have parallel plates with charge stored on them, and the voltage is the energy per charge, and my brain's sort of dropping right out of my head here, but it's not going to help you because the volts per meter and what is it? QC is the other one. QC? No, my brain's really dropped out of my head. It's funny you swap your focuses. Should be able to do this better. It's early morning and I'm not feeling well. We'll give myself a pass on that. But you still have the same problem. You could ask this in a level 2 context here, and you've got this and what happens when you separate that, but it probably wouldn't be that fair. That's how I'd approach it. Maybe you've got some other ideas. Maybe you want to discuss the level 2 stuff. Put some stuff in the comments. Have a bit of a discussion about it. D, and then experiments with connecting some different capacitors in series and parallel across the 12-volt supply, as shown in the diagram below. Calculate the voltage across the 4.70 times 10 to the 2 microfarad capacitor. That's this one here. Begin your answer by calculating the total capacitance. This is quite interesting, actually, because you'd be familiar with doing these with resistances for level 2, but you don't typically do this kind of question for capacitances. When you start calculating the resistance, the capacitance in parallel. So remember, in parallel, it's the resistance in series, similar one. So you go, I keep going back to it. So C1 plus C2, and then whatever the capacitance of that in the parallel part is, you're going to, I'll call this C3. It's going to be 1 over C3 plus 1 over CP equals 1 over the total capacitance of the circuit. So that's your first part there. Normally we'll be working in current flow, but now we've got to work in terms of charge. So we'd have to work out the charge stored for the total circuit here. So we'd use the total capacitance and the total voltage to find the total charge stored, and then that charge is going to divide up according to the ratio of the capacitances here. So once you've got that, do we have? Yeah. So we've got V and we've got T, and we find Q. And then you can follow, same as you would with the ratio of the resistances, the proportion of that to that will have the two different charges. I have to go, there's a small child coming. Hopefully that's enough to help you work out the last part. Again, throw some stuff in the comments if you have questions, and the community, as they watch this, can help each other. And you can wait also and see the answers that come out. This one's a little bit, I think this is a fair question, but it's definitely a tricky one. And it would have helped you to go through the derivation of these, of the capacitance formulas in series and parallel, in the same way that hopefully your teacher would go through the resistance formula derivation using current rather than charge. And you would then pick it up. Like if you followed that, you'd hopefully have a bit more of a clue when it comes to this question. Right, all the best. Get some comments going. Subscribe if you find this helpful. And although most of you will be moving on to university or something if you're doing this and you're interested enough to listen all the way through to this stage. But yeah, maybe you can recommend it to others if you found it helpful. Others who are coming through to level 3 in future years to you. All right, cheers. See you later.